the commutative law of multiplication does not generally work for symmetries. And you might think that if that's the case, this couldn't possibly have anything to do with nature. But can I borrow your book? Just we'll give it right back. Or crumple. Okay. All right, here's a book. There's the x-axis, there's the y-axis, there's the z-axis. I'm going to rotate about the z-axis. Now I'm going to rotate about the y-axis. Book ends up like that. Hit the reset button. Now I'm going to rotate about the y-axis, 90 degrees. And now I'm going to rotate about the z-axis, 90 degrees. Ends up like that. So what do we get? First time around I did z, y, got this. Yeah, the binding's back here. Second time, I first do y, followed by z. Ends up like that. This versus that. A times b doesn't equal b times a in nature. I'm sure you learned at some point the commutative law of multiplication in school. 3 times 4 equals 4 times 3. Didn't somebody tell you that law at one time? It also applies to addition. 3 plus 4 equals 4 plus 3. To me, that's a content-free statement until you give me an example of something in which it doesn't hold. And here's an example. Symmetries in Jeddah, this is an astonishing result we have here because this is also a magic square. Notice that every element of the this is called a group. Every element of the group appears once and only once in every column, and it appears once and only once in every row. That fact is what mathematicians exploit to be able to construct groups in general and to prove theorems about them, because it's a powerful constraint. Not just any old multiplication table can be a symmetry. It has to have certain well-defined properties. And I just showed you the book rotation doesn't commute, so it's got something to do with nature. Okay, so are you astonished by this? There's one other fact about this I should tell you. Group multiplication is associative. But it shows you how subtle the concept of associativity is. Let's think about that for a moment. Well, you know from school that 3 times 4 times 5 equals, what, 60? That doesn't matter as to how you do the multiplication. You can multiply 3 times 4, which is 12, then 5, which is 60. Or you can do 4 times 5, which is 20, times 3, which is 60. Doesn't matter how you do it. So in other words, A times B times C equals A times B times C. But if you think about what you're really doing here, it's quite complicated. What you're doing in this case is you're starting with A, following it by B, and getting a result in the bracket. Then you're following it by C. That's pretty simple. But over here, you're starting with B, following it by C, writing the result down on a piece of paper, hitting the reset button, doing A, followed by what you wrote down on the piece of paper. Okay? So when you think of associativity, it's quite tricky. But if you can check that this multiplication is associative. All useful stuff in physics so far has been associative. Now, it's easy to see a non-associative system. I want you to always, when you hear the teacher tell you, well, that's associative or commutative, try to think of something that isn't. Can anybody think of a non-associative operation? Well, what people call, slash division. Okay. You'll get a different answer if you do 3 divided by 4 divided by 5 in that order, as opposed to doing 4 divided by 5, remembering the number, then dividing 3 by the number you remembered. In other words, this does not equal this. And that's the paradigm for all non-associative systems. They're called norm division algebras. But they don't appear to be useful in physics. This is. And all symmetries are associative, but they're not generally commutative. Now notice there are subgroups in here. If I just ignored the reflections, I just have rotations, and they form this little 3 by 3 bit up here in the upper left corner. And they also form a magic square, and I can do A times B and get C. And so that forms the set of rotations in the plane. The set of rotations in the plane form a symmetry group. But it's sitting inside of a larger symmetry group once you allow the reflections, which sort of require you to come up out of the plane and go back in again. And actually, this is an example of a commutative group. These rotations in the plane do satisfy A times B equals B times A. So symmetries often have subgroups. And notice there's also something here we call parity. This thing knows about the difference between what lives in the plane and what doesn't in a basic way. Suppose that we identified all the rotations by the number 1. Then 1 times 1 would give back 1. But we could identify the reflections by the number minus 1. Then minus 1 times minus 1 gives back plus 1, a rotation. Furthermore, 1 times minus 1 gives minus 1, which is a reflection. So we say that the reflections have odd parity. They're different. The triangle knows, although it has this symmetry, that some of the operations are different. Those are the ones that you have to lift out of the plane and come back to. And all of that is encoded in this remarkable structure. Now let's talk for a moment about the continuous symmetry. So here I have basically this is the equation of a circle. So I would have a circle of radius 1 here. And I take a given vector whose x-axis, whose x-coordinate is x, y-coordinate is y. And if that vector lies on the circle, then x squared plus y squared equals 1. I can do a symmetry transformation that rotates the circle into itself and rotates that vector through an angle theta to a new vector. The new vector will have x prime and y prime for its coordinates, and that new vector must satisfy 1 equals x prime squared plus y prime squared, because it's on the circle. What's the transformation? Well, this, of course, is the heart of trigonometry. The new coordinates, y prime and x prime, are related to x and y through these equations. Y prime cosine theta plus x prime sine theta gives the new y, gives the old y. X prime cosine theta minus y prime sine theta gives the old x, and you can check that. But here we have an example of the symmetry of an equation. So in physics, we might have an equation like F equals ma or something like this, and we notice if we take the variables in the equation and we replace them by new variables through this relationship, we get back the same equation. And it's easy to check that by taking x and substituting x prime cos minus y prime sine, taking y and substituting y prime cos plus x prime sine, forming the squares, doing a little algebra, using the fact that cosine squared plus sine squared is 1, and you'll see that x squared plus y squared equals x prime squared plus y prime squared. So what we have found here is a little more abstract. Yes, there's an underlying geometrical picture of what's going on, but the equation written in these variables is the same as the equation written in those variables. And this is a coordinate system independent equation. It really says that it doesn't matter which variables you use. You could use these variables or that variables to talk about a vector because they're related by the equivalence transformation, by the rotation of the circle. We'll come back to an application of that in a moment. So what the mathematicians were able to do was to classify all continuous symmetries. And they did this in the 20th century, late 19th, early 20th century. What they found is that the continuous symmetries form 4 classes. And basically, these are kind of the basic things you can build. You can build up more symmetries from this. But the simplest is starting with the circle, which is called SO2. You can go to the sphere, which is SO3. You can go to the 4-dimensional sphere, SO4, and so forth. So spheres in any number of dimensions form symmetry groups.